Okay, I hope my PDF is visible. So can you see the document PDF?
Yes, sir.
Okay. So yesterday we have done design of.
Sir, can you turn on the recording?
Already done. Okay. So
yes, sir.
Actually we were seeing this design of beams for shear, and problem we have done, and I just showed you a general outlay of how to draw the diagram. I mean, how to give the drawing for that. So that particular aspect also, just like everything else, you also have those details in SP34. Okay, so if you come to page, this is page 101. So if you come over here, you have a section on detailing of shear reinforcement. Okay, some general aspects about it are given. So every shear reinforcement, the stirrups are in the form of closed rectangular hoops. Okay, so how to take a hoop and how to make the hoop. So some typical techniques are shown over here. Okay, different ways of anchoring the ends of stirrups. Okay, like this they have shown 3 different methods. The most common method is the one 8.5B. Okay, this is the most common method where you take the bar, then bend it around the top reinforcement, bring it down, and then do the same thing over the bottom reinforcement, bring it up, bring it back, and then again bend it on through the top bar on the same bar. Okay, so this is the most common way. There are other ways also whereby you can, instead of just hooking it by bending it inward, you can just make it right angle bends and do it like this also. This is less common. C is even less common, where they do it like this, where they take a bar, bend it up, bring it, come down, and then hook this end of the bar with the first hook. Okay, so it's like bringing it around and hooking it like this. Okay, so this kind of a bend is also, it's specified here, but nobody does this. The most common one which is done is this 8.3. This is the easiest thing to do. So how much to bend it? You cannot just make a very small bend and then call it as a proper hooking, anchoring. You cannot do that. To get proper anchoring of the stirrup, this bend, this hook, the length of this hook should be at least 6 times the diameter of the stirrup. So if it's an 8 mm bar that you're using for the stirrup, this bend should be 48 mm. Okay, so that's the minimum. These things and all you need not mark in the drawing. These are things that the person who's doing the bar bending should take care of. Okay, as far as your structural drawings are concerned, you need not actually show these dimensions. Okay, but just for your interest, I just showed this. The things what you're actually required to show in your detailing are the remaining things. Okay, which is, for example, this is how you draw your longitudinal section of your beam with stirrups. Okay, so you have the bottom bars, and if you have negative moments, you'll have a bar at the top. You'll be doing this bar bending and all these things which you already seen when doing the slab drawing. The same thing. So you'll have top reinforcement, bottom reinforcement in the longitudinal directions. And then if you have a look over here, you can see here the stirrups are very closely spaced, and inside the spacing seem a little bit wider. And then once again, when you come near the support, you have closer spacings. Away from the support, you have larger spacing on the stirrups. Okay, so therefore, it is always true that generally, practically, people when they give stirrups, they will give a close spacing within the close to the support, and away from the support, they may double the spacing, or even if not double, it will be definitely at least much more than the spacing which is given near the support. Okay, so this is how you draw. So this is the entire detail of the beam. Okay, it has longitudinal reinforcement, it has shear reinforcement. Okay, so everything is there. So this is the proper full detailing of a beam. Okay, and depending on how many legs you have for the stirrup, you will have different rearrangements. So this is the 1, 2, 3. This is about, I think, 6 legs. This is a 4-leg stirrup. This is also 4-leg stirrup, 8.8C. Okay. So these are some arrangements you can do. The only thing you should avoid is you should not have any stirrup arrangements where there is an overlap. Okay, meaning that here you have these two stirrups overlapping, so that you should not do. But otherwise, you can, depending on how many layers of bars you have, that many stirrups you may have to be required to give. Okay. Then one more important thing which we did not, something we were looking, the maximum spacing. This is something we were thinking about yesterday. So when you did the problem, we found out the spacing was something like 500 mm or something when we used 500 yield stress bar. So we made that calculation, and then you got some big spacing. What 500 something? No, how much was it? The original spacing that you got yesterday with the FE 500 bars for the stirrup. Some big spacing you got. No, anybody remembers? Can you look at your notebook and tell me how much it was?
512, sir.
512. Okay, so you were thinking the 512, you should not give 512, it should be a 300 or something, I told you. Okay, actually 300 is not a limitation, but the reason why I thought it was 300 is among all the drawings that I've seen so far, in all the checks that I've done, I've never come across a stirrup which is spaced more than 300 mm apart. So I assume that would have been the limitation, but that's not the limitation. Actual limitation is 3/4 of the effective depth of the beam. Okay, our beam yesterday was about 400 mm or 410 mm effective depth. So 75% of that is same 300. So the actual maximum spacing requirement, which is limitation, which is given for stirrups, is either 3/4 of the effective depth or 450 mm. Okay, whichever is lesser. Okay, so that is the maximum spacing. So 450 mm, the most practical thing to do is never go more than 250 mm, 50 mm, 300 mm. I've rarely seen people give larger spacing for stirrups. Even if there's very low shear, people still give that at least that much spacing for stirrup. So you also, in case you have a problem in your tests or something, and you get a very low shear to be resisted by the stirrup, still give at least 8 at 250 center to center or something like that. Don't just give very large spacings or avoid giving stirrups. Okay, don't do that. So these are things like there. Then these are some special considerations. If somebody is bored, they can go through this. Otherwise, no, you can just move ahead. So this gives you all the details of a beam. Okay, details with regard to flexural reinforcement, details with regard to shear reinforcement. All these details are given over here. Okay, so you have the maximum compression steel that you can give, maximum tension steel that you give, maximum stirrup spacing that you can give. Okay, cover to the stirrups. So everything is given over here. So this is a very in-depth beam. You can just make like this. So this is how you give all your reinforcement for your for shear. Okay, so in general you give about this distance is, I suppose, about 1/5 from this end and 1/5 from the other end. For that much spacing, for that much length, you have to give a close spacing of stirrups, and the remaining can give a wide spacing of the stirrups. I suppose it's 1/5 of the distance. Let me just have a look. This is beams. This is a usually pretty good guess. 1/5 of the length. So just have a look at this. So when you're doing your when you're asked to detail your problem in your test and those things, so detailing carries marks. It's important to do it properly. It's important to do it neatly, and with all necessary details should be given. Unnecessary details should not be given. Okay, that's the trick of doing detailing drawings. Okay, if you give too less detailing, then something is missing, and actually carrying out that activity will not be done properly. If you give too many details, it confuses the person who actually go to the field and carry out the work. Okay, so give what all are importantly needed. For example, don't give these details. The length of the hook and all don't give in your drawings. Okay, that and all is not needed for your purpose. In fact, nobody will even do it in a structural drawing. It is the job of the bar bender. Okay, so these details and all don't give, but these details should be given. Okay, how much is that? Not this one. These details should be given. Okay, how much spacing of stirrups, how much bottom reinforcement, how much top reinforcement, the depth of the beam, and all those things should be given. So give the necessary details, don't give the unnecessary details. So that's about this drawing. So we'll move ahead with the next part. Okay, so hope I have shifted to the PPT now, which is visible to you now.
Yes, sir.
Okay, so the next part after shear is torsion design of beams. Now, as far as flexure and shear are concerned, bending moment and shear force will always 95% they will exist in all the beams. Okay, so whatever beam design you do, design for shear and design for flexure is something that you will inevitably you will be doing that design. However, torsion design is not something which is always going to be present. Okay, you need to only for specific cases in beams and specific arrangement of beams alone, torsion will be there. Otherwise, torsion will not exist. Okay, and you need not do this torsion design unless it is specifically you are able to judge that a particular beam is going to be subjected to torsion. So where does the torsion come from for a beam? Okay, so that's the thing that you first have to detect, because unless you know that a beam is going to have torsion, you will not have an idea whether to do that design or not. So how to judge that? The one easy way is, look at this particular picture. You have this is like a bus shed or something. Okay, so there's a column, two columns supporting a beam, and over the beam there is an overhanging sunshade or whatever it is, or a shell or a roof cover is there. Okay. Now this roof cover, it's not very heavy. It doesn't take any load above it except wind or things like that. So, but anyway, still there is some load which acts through this sunshade. Now, if you look at this, part as a cantilever, for example, this is a fixed support, and this sunshade is a cantilever. At the fixed end of a cantilever, what do you have? What is present at the fixed end of a cantilever? What type of forces there at the fixed end of a cantilever? Simple strength of materials. At the fixed end of a cantilever, what are the forces that are present?
So the support reaction force.
Support reaction and
the bending moment.
Support reaction and the maximum bending moment, which is also the moment at the support. Okay, so the support will have a moment. So it is like, so imagine that this whole beam is the fixed end of a cantilever, and this whole sunshade slab is one particular cantilever. So the end of a cantilever, as you said, will have a reaction moment or support moment. So imagine that there's a support moment all across this entire beam. Okay, so it's a moment. That particular moment will try to twist this beam. Or in other words, this beam will be subjected to torsion because of the support, because of the moment generated by this object, this roof cover or whatever. It generates a moment at its end, and at the end of that roof there is a beam. So that beam will have to take the entire moment. I mean, as far as the sunshade is concerned, it is a moment. As far as the beam is concerned, it becomes a torsion, okay, or a twist. So this type of torsion, which is caused directly on the beam, is known as primary or equilibrium torsion. So it is caused directly by the bending moment in the member supported by the beam. So this beam is supporting a member, and that member is causing torsion on the beam. For example, bending moment in a slab or sunshade acts as a torsion along the whole length of the beam. The value of the torsion on the beam equals the value of the bending moment at the end of this sunshade. Okay, so whatever the bending moment caused at the fixed end or at the support of this cantilever, that bending moment at the end of the cantilever is the torsion, and it's equal to the value of torsion at the beam. Okay, so this is known as primary equilibrium. It's called as equilibrium torsion because it is, you're saying the bending moment, which is it's a force quantity. Bending moment is it's something related to forces. Okay, so the bending moment in one part becomes the torsion in another part. So it's basically moment equilibrium. Okay, so that's why it's known as primary or equilibrium torsion. The second one is known as secondary or compatibility torsion, where difference between equilibrium and compatibility are like they are two aspects of the same thing, or they are counterparts of each other. While equilibrium talks about moments, forces, etc., when you come to compatibility, it talks about displacements and rotations. Okay, so you see, all forces or all moments should be, summation of moments or summation of forces should be 0, or they should be equal. You say that is called as equilibrium. But the same thing if you say all the rotations should be the same or all the displacements should be the same, that is called as compatibility. Okay, so it's just a different aspect of it. So for example, if you look at this system, there is one long beam going this way, and similarly another beam parallel to that going this way, and in between them there are several secondary beams spanning between them. Okay, so there are secondary beams spanning between two primary beams. Okay, now and on top of these primary and secondary beams there is a slab. That slab will try to bend this secondary beam. Okay, it tries to bend this secondary beam. When the secondary beam bends, it will try to rotate this primary beam. Okay, so therefore, if you have a system like this, whatever rotation happens over here in the secondary beam, this primary beam also should rotate by the same amount. Okay, secondary beam rotates, primary beam should also keep up with the same rotation. Okay, so that is known as compatibility or secondary torsion. At the joint of a primary or secondary beam, the rotation has to be the same. If the rotation is not, if this is rotated by a different amount and this is rotated by a different amount, that means the secondary beam and the primary beam have separated. Okay, which means that's bad. Okay, primary beam and secondary beam cannot separate from each other. If that happens, that means it's broken. So that should not happen. So whatever rotation the secondary beam undergoes, the primary beam should also undergo. So that is known as secondary compatibility torsion. When the secondary beam rotates due to the load, the primary beam must twist by the same degree. And because of this twisting, there is some torsion which is induced. Okay, I hope you people know this equation. Have you come across this equation? Have you come across this equation or not?
Yes, sir.
Yes, sir.
Yeah, you should have come across it. Okay, so you had mechanical solids, you also had a strength of material slab as well. So I think you would have come across this. Anyway, this famous formula is suitable one. It is true only if you have a solid, no, not solid, it will be even hollow, but it should be circular. Okay, otherwise this equation cannot be used because your J will not be easily found. Okay, if it's not circular. So designing of the torsion is very similar to actually doing this, except that just hold on, sir. டிபார்ட்மெண்ட் இருக்கு சார், ஒரு 20 minutes கிளாஸ் மட்டும் இருக்கு, அதுக்கப்புறமா வந்துருக்கு. சொல்லுங்க சார். இங்க நீங்க நீங்க ரூம்ல தானே இருக்கீங்க? சரி, ஓகே, நான் வந்துடுறேன் சார், கிளாஸ் முடிச்சுட்டு. ஓகே சார். Okay, so it's the same thing as doing for a circular bar, except that it's a little bit different because your RCC beams are usually rectangular. Okay. But the main thing that you should realize is, so if you look at this formula, T is torque, J is your polar moment of inertia, R is your, it's the point along the radius, that is R. Tau is what kind of a stress is tau? Is it normal stress? What kind of stress is tau?
Shear stress.
It's a shear stress, meaning that torsion causes, it induces shear in an object when you have torsion. So torsion design is just an extension of design for shear. And therefore, when you look at a beam which undergoes torsion, your cracks will be, one thing is it will go all around your beam. Okay. For normal shear, your crack will start at the bottom and go to the top. Okay. So that's what will happen. But when it is torsion, you will have cracks all around the beam. Okay, and those will be inclined at 45 degrees, more or less 45 degrees. Okay, so cracks inclined on the top. If you have inclined cracks on the top face and the bottom face, okay, I'm not talking about the side face. I'm talking about the bottom and top. Okay, so you are used to seeing the side face cracks. Okay, if you look at the side of the beam, and then you see vertical cracks, you say it's a flexural crack. You see 45-degree crack, you say it's a shear crack. But those views that you have seen are the side of your beam. I've till now not showed you any view of cracks from the bottom or from the top. Okay, so this is one such view I'm showing from the top of a beam. Okay, so if you look at the top of a beam and the bottom of a beam, and you see that top and bottom faces also you have inclined cracks, then it is indicative of torsion. Because your regular shear cracks will be, it will have inclination only on the side face. It will not have an inclination on the top and bottom. Okay, so this is a minor. This is kind of a difference between your normal shear cracks and your torsion cracks. Okay, so next, how do we design for torsion and what are the different modes of torsion? And some of the occurrences of torsion are shown over here. So, for example, you have a space frame like this. Okay, so you have a beam over here, a beam over here, and a column over here. Each of this will cause torsion on the other. Then, of course, you have an inverted L beam. So, if you have a load supplied over here, this part will undergo a bit of torsion. A curved beam will undergo torsion, and the H beam in a slab will undergo torsion. Okay, and torsion, we know it's something which twists. Okay, so you can actually idealize so if you have a twist T going like this, you can assume that this rectangular beam is going to resist your torsion by generating a couple in the opposite sense. So if you have torque acting clockwise, you will have resistance generated counterclockwise. Okay, and it is assumed to act as a single closed loop. Okay, and this loop of forces going around the object, that is known as a shear flow. This is a bit of an advanced concept. I don't want to go too much into shear flow. I will just leave it by saying that when you have a torque acting in a particular sense, you have a resistive couple generated in the opposite sense. Okay, which acts inside which is present inside the cross section of that particular beam, and that flow is known as, you can just call it a shear flow. I don't want to talk too much more about it. It's if I start talking about this, I'll deviate from RCC and go to advanced mechanics. So I don't want to do that. I'll leave it at this. So what happens is we use this theory called as skew bending theory. Skew means it's distorted. That is the meaning of skew. Okay, it's not straight. It's not parallel and perpendicular. It's kind of oblique. That is the meaning of skew. So we have some assumptions when using this theory. We assume that our compression steel is much less than our tension steel, and we assume that when torsion occurs, the compression phase becomes a bit skewed, or it kind of it undergoes that kind of distortion, okay, or that deviation. So based on this skew bending theory, we will be able to identify 3 different types of torsion failure, and this torsion failure will depend. The type of the torsion failure will depend on the aspect ratio. Aspect ratio means breadth to depth ratio. Okay, breadth of the beam, depth of the beam, that ratio. The ratio of the compression steel to the tension steel, and finally the ratio of the bending moment to the torsion. Okay, so bending moment you will have, and in case you have some torsion, how much is the torsion in relation to the bending moment. So these are the three different aspects on which the type of torsion failure will be influenced. So based on that, the first mode is known as a mode 1 type of failure. This occurs when you have, this is the most common type, and it occurs when your bending moment is much larger than your torsion. Okay, or in other words, torsion is there, but it's not too much. Mainly it is just bending moment. So in such a case, you will have mode 1 type failure. So in mode 1 type failure, your compression phase, so this is your loads are acting from top to bottom, and your compression phase becomes skewed, but it's still, the top phase still remains on the top. Okay, this is top phase, it still remains on the top. Okay, the sections are not narrow, meaning that there is a relatively good amount of breadth in the beam. It's not a very narrow beam, which is having very small breadth and very large depth. It's not like that. It has a good amount of breadth and a good amount of depth. Okay, so it's not a very narrow beam. So in such a case, you will have cracks starting at the bottom. Okay, it will start at the bottom and keep propagating to the sides and go all around. Okay, so this is mode 1 type failure where it is happening for very low values of torsion in relation to the bending moment, and it's the most common type, and it's the most easy to address type. The second is known as mode 2 type of failure. Okay, in this phase, your bending moment and torsion both become comparable. Okay, torsion is not very low compared to your bending moment. It also starts to compete on a pretty competitive nature with your bending moment. In such a case, because your torsion is relatively good enough, or relative, I should not say good, it's relatively big enough. So therefore, the torsion is that much that that face which was on top originally, it twists and it falls to the side. Okay, it's almost like the face which was like this, top face which was like this has twisted. Okay, so that kind of a twist happens. This will happen when your sections are a bit narrow. Okay, this compression phase becomes skewed to the side. Okay, and this failure is by lateral bending, which means the bending phase becomes lateral. Okay, so generally you're used to saying that when you have bending, top is compression, bottom is tension. Okay, this is what you're used to saying. But because of torsion, what happens is what was top and bottom, it twists and becomes, this side is compression, this side is tension. Okay, instead of top and bottom, left and right becomes tension and compression. Okay, so that's why what I mean by bending phase becomes left and right instead of top and bottom. Okay, so this is a very bad to even think about and look at. Okay, so this is it's something which is it should be avoided. Mode 2 type of failure, if you cannot design for this. Okay, so if at all somebody is going to see that a mode 2 type of failure is happening, then the only thing to do is redesign the whole thing. Don't make it happen like this. So the cracks start at 45 degrees at the sides and then propagate to the bottom and top, because top and bottom have become the sides. That's the reason. Worst of all is mode 3 type failure, where its top has become bottom, bottom has become top. Okay, very large torsion and very less bending moment. Okay, cracks instead of starting from the bottom, crack will start from the top and come to the bottom through the side. So this is known as negative bending failure. Okay, and because the cracks will occur opposite to what you expect. So you would have designed for a particular load. Okay, and so you'll be thinking that okay, from the bottom to the top, the cracks, I mean, you don't want it to fail, but whatever you learned from limit state method is, or in general bending failure is, cracks start at the bottom and go towards the top. That's right, and that's what everybody knows. But what happens if you have such a big torsion that it has kind of rotated your beam upside down? Okay, so that is what is actually, I mean, you will not see this anywhere happening in real. If it happens in real, that means 100% that beam has collapsed. Okay, whatever was above it would have also collapsed. Unless there's a collapse, you will not see this. Okay, anyway, this is in the unfortunate situation that this happens. This is known as negative bending failure because it's the negative of what you normally have in flexural failure, or the opposite of what you have in flexural failure. Okay, this also happens when you have very narrow sections and a good amount of torsion. So these are the three different modes for torsion. Now, how do you design for torsion? As I told you, design for torsion is again, it's to resist shear stresses. So therefore, still it is, you have to find a shear stress based on the torsion and then give it accordingly some stirrups. Okay, so stirrups may be such as to interpret the diagonal cracks, okay, from the torsion and also from the shear. And whenever you have torsion coming, one important thing is whether you by design you have it or not, you should always give 4 bars at the corner. Okay, 1 bar here, 1 bar here, 1 bar here, 1 bar here. At the corners of your beam, you should always have some bars, longitudinal bars. Okay. By the nature of designing for bottom reinforcement and top reinforcement itself, you may have some bars. But in case you don't have any bars at the top, you still have to give it. Okay. And you should have relatively good bars at the top and bottom at the corners so that you have a path around which the torsion can flow. So when you give 4 bars like this, you can imagine like the shear is going, the torsion is going to flow or go around like this. Okay, so to guide that path, you have stirrups and you need this longitudinal bars. So the spacing of these 2 bars, x0 and y0. So why is this x0 and y0 is needed is because based on that only you will calculate how much is your area of torsion reinforcement that you need. The torsion resistance is not much dependent on the core area, thus it's idealized as follows. Meaning what I'm saying is the torsion resistance of a beam is not, it doesn't depend on how much, what the size of the square is or how much concrete is there within this area. That is not important. What is important is how much perimeter is there. Okay, how much perimeter is more important than how much area is inside for torsion resistance. So critical section, it's the same as for shear. Okay, D from the face of the support. So I said when we are designing for torsion, basically we are going to convert it into a shear stress, and also we are going to find an equivalent bending moment as well. Okay, so you have to find 2 things. When you are given a particular torsion, so based on the torsion, find out what is the shear stress or the equivalent shear which is caused by that particular torsion. So this is the formula. V from the torsion equals VU, or the equivalent shear equals VE equals VU plus 1.6 times TU by V. Now what are the terms? VU is what you saw yesterday. What is the actual shear force from the load? Okay, this is not the torsion converted shear. This is the actual shear which is present at the support. So what is that? Okay, so that is VU. Then the second term is the part of the shear which is caused by the torsion. So how to find that part of shear? That is given away 1.6 times. This is empirical. This 1.6, there's no analytical meaning to it. So 1.6 times torsion by B, where B is the breadth of the beam. Okay. So when you do this, of course, maintain units, okay, in kilonewton meter. Maintain units in kilonewton meter and then carry out this calculation. And then, of course, similarly, you have to do it for the bending moment, where I say the equivalent moment equals mu plus mt. Mu, you know what it is. It's the same moment which, for example, in the simply supported beam which you are calculating, factored load, it's W, then you do WL squared by 8. Okay. So which is the one which you want to design for. So that moment is mu. Plus how much equivalent moment is caused by the torsion. to do that again, that MT equals TU times 1 plus D by capital D, not small d, capital D by B divided by 1.7, where capital D is the overall depth of the beam, not effective depth. B is the breadth, 1.7 is an empirical constant. Then you find this value, add it with this. Okay, and then find out like how much is the torsion. Okay, so this is how you design for torsion. It's basically the same as doing a torsion design for. It's basically a combination of design. It's very easy. Find the equivalent. Find the shear force caused by torsion. Find the bending moment caused by torsion. Add them with the actual shear force which you have, and add the moment with the actual moment which you have. Then design for this moment and for this particular what is this shear force. Okay, and what is the formula? Formula is also pretty easy. It's a very small formula. Okay, it's present over here. The formula is not a very big deal. It's very similar. The problem we'll be doing tomorrow. Torsion. Okay, so I hope you'll be seeing my IS456. So this is part of torsion. So this formulas I showed you, B equals U plus 1.6 TU by B, and then equivalent moment also I showed you. So how to calculate the torsion reinforcement? Okay, it's given by this particular formula over here. ASV equals TUSV by B1 D1 0.81 Fy plus VU SV divided by 2.5 D1 0.87 Fi. So you are more familiar with what you saw yesterday for normal shear. Okay, where is that? So it's very similar to this, except that you have two terms instead of one. Okay, so that is the only difference that you have. And otherwise, no, there are two terms because one term takes care of torsion, other term takes care of the direct shear which you have. So that's why you have two terms. And this also, it's very simple. You can assume some ASV dimensions and all. You will know what is the actual torsion. You'll know what is the actual shear. Okay, and then from that you can just find out what is SV, and you can give that as your spacing, and make sure that it's at least this value. Okay, spacing should be at least this much of value. Okay, otherwise everything is same. Spacing also you have some very similar requirements. Okay, this is spacing for torsion reinforcement. The transverse reinforcement for torsion shall be rectangle closed stirrups placed perpendicular to the axis of the member. Spacing of the stirrups shall not exceed the least of these three values: x1 plus y1 by 4 and 300, where x1 and y1 are the short and long dimensions of the stirrup. So, for example, if you have a beam which is 300 by 400, okay, then you're having 50 as cover. Okay, then it becomes 200 by 300. So x1 will be 200, y1 will be 300. Okay, so your stirrup is a rectangle, no? The short side and the long side of the stirrup, that is x1 and y1. Okay, so these three values, the spacing of your stirrup should be lesser than the least of this. Okay, so these are the requirements as far as the reinforcement are concerned. I'll stop with this. Tomorrow we'll do a problem on torsion, which will be a kind of complete problem. Once you know design for torsion, that means you can do any beam design. Okay. Anyway, I'll end the meeting. So some of you have to go for a quiz. Let's say 4:45 exact. Okay. So I'll see you tomorrow, and we'll do a problem. Okay. Can I close?
Yes, sir.
Yes, sir.
Okay, fine. See you tomorrow then.